And this is page 100. So we're looking at energy in chemical reactions, and the two main types, which I hope you guys all know by this point in your lives, are kinetic and potential. Tell your partner what kinetic energy is and what potential energy is. Page 100. Okay, those of you taking physics probably know way more than I do about energy because I've forgotten everything, but kinetic energy essentially is the energy of motion, and potential energy is energy that is stored, okay? Do you know the law of conservation of energy? Energy cannot be created nor destroyed, only transformed from, oops, this little one over here needs to be put in a better place. Only transformed from one type of energy to another. So in the universe, the total energy is equal to the kinetic plus the potential, and that's what's going to become useful for chemical reactions. The total energy will remain the same, but kinetic can be transformed into potential, and potential can be transformed into kinetic. Energy is measured in joules or kilojoules. Now, in chemistry, there are three main types of molecular motion. There is vibrational, and there are many types of vibrating. So there is bending, like this. Everyone do bending with me. Bending. Then there's symmetric stretching. Okay. And then there is asymmetric stretching. So if you imagine we're a CO2 molecule with the C in the middle and the two O's, the O's can go up and down, the O's can go in and out, or the O's can kind of go side to side. Yeah? If you really want to get out of your chair and try rotational motion, you can do that. There's rotational motion in all three directions, X, Y, and Z. I don't know why I only have X and Y here, but that's okay, whatever. Oh no, it's because it can but it can also yes? Okay. And then of course, translational motion is where it moves, so it can be moving and rotating and vibrating in all sorts of dimensions and things like that. Now, the faster that these molecules move, the more kinetic energy they have. Do you guys know how we measure kinetic energy in chemicals? We have a tool that we can use. Thermometer, yes. Temperature is literally a measure of the average kinetic energy of a system. I'll call it a sample, okay? Doesn't matter. You're not going to have to define it. You just need to know it, okay? Oh, look, temperature is a measure of the average kinetic energy. Why do I write things down? I don't know. I usually have them written below or on the next page. So the more kinetic energy, the higher the temperature. Yes? More kinetic energy, higher temperature. So faster molecules mean you have more kinetic energy, which means you have a higher temperature. Slower molecules, less kinetic energy, lower temperature. Potential energy is the energy that is stored in atoms and the bonds between atoms, and it can be released or absorbed. No, I'm going to say released. That's okay. Released or formed. Formed. There we go. By various chemical reactions. Chemicals with a high potential energy are less stable. So, if you think about a ball at the top of a hill, that is less stable than a ball at the bottom of the hill. So just like the ball has higher gravitational potential energy at the top of the hill and lower gravitational potential energy at the bottom of the hill, less stable, more stable, it works the same way with chemical potential energy, okay? Things with high potential energy, less stable, low potential energy, more stable. And electrons and atoms are always spending a lot of their time just trying to get to a more stable state, okay? Now, if we take, in a chemical reaction, if we take some kinetic energy and we transform it into potential energy, what's going to happen to the molecules? Will they move faster or slower? They're going to move slower because our kinetic energy is decreasing, right? And our potential energy is increasing. So the molecules are going to move slower, which means the temperature will drop. It's going to decrease. What happens to the total amount of energy? Stays the same. Now, what if we take potential energy and we transform it into kinetic energy? The particles are going to move faster. The temperature will increase, and the total amount of energy will remain the same. Okay, so in this case, the potential energy decreases and the kinetic energy increases. Which of these two situations is an endothermic reaction? Which one is exothermic? Have a chat with your neighbor about that. Which of these is endo or exo? Okay, let's take a little vote. Is this top one, we're going to vote for endo or exo, and the sign for N is like this. You put your 2 fingers over your thumb. That's an N. Show me an N. Okay, that's an N. 2 fingers over your thumb. And then an X is like that. You stick your thumb out and you curl your pointer finger. That's an X. Show me N again. X. N. X. N. N. X. Okay. So you get to vote for either endo or exo for the top one, or you can also vote, I don't know yet, right? I'm here to learn things I don't know yet, which is totally fine. 5, 4, 3, 2, vote. First one. I've got some of each. Ooh, I got a mix. Okay. Well, we'll discover, won't we? Okay, so let's take a look. Let's take a look and see what happens. Say you have some reactants in a chemical reaction that have 2 kilojoules of potential energy. That's just energy that is contained in those bonds. It's like saying this hamburger contains 400 calories. That's the amount of energy in it that can be released, yes? So these reactants contain 2 kilojoules of potential energy. Now let's say that the products contain 12 kilojoules of potential energy. That means that the products have 10 more joules of potential energy than the reactants. Where did that extra energy come from? This is energy that is not contained or stored. This is energy that is not stored in either the reactants nor the products. What kind of energy does it have to be? That has to be kinetic energy. Yes? So what is happening to that kinetic energy as we move from reactants to products? As reactants are transformed into products, what is happening to the kinetic energy? It transforms into potential energy. Hi. Let's see who we've got. We've got Sylvia and Tiago. They're both here. Thank you. Sylvia. This one is convenient. And Tiago. Just when it's convenient. This kinetic energy is being transformed into potential energy. So what is happening to our temperature? The temperature is decreasing. Is energy going into this reaction, or is energy coming out? Which side is the kinetic energy on? It's on the reactant side. So it is going in to the reactant arrow. And when energy goes into the reactant arrow, that is endothermic. Okay? So when we have an endothermic reaction, the temperature gets warmer or colder? It gets colder. right? Because you have the molecules are moving less quickly now because that kinetic energy of motion has been transformed into stored potential energy. So you can recognize an endothermic reaction because it's going to look like A plus energy gives B. The energy term goes into the reaction. All right. Now, we've just kind of written all of this on here. The total energy before is the same as the total energy afterwards. And we can show this on a graph. So here's our graph, and what we put on the left-hand side is the potential energy on the y-axis. And we say this is the direction of the reaction, which just means the reaction is going forwards from reactants to products. We start with reactants, we go towards products. The reactants have 2 kilojoules of potential energy. The products have 12 kilojoules of potential energy, and 10 kilojoules of kinetic energy are absorbed and transformed into potential energy. Now, do you remember I told you about this and how this sometimes confuses students because they say, oh, energy is absorbed, it must get warmer. Yes, but the thing to remember is it's not just being absorbed, it's being absorbed and transformed. Okay, and it is this transformation process that means you have less kinetic energy, the particles are moving slower, and so it feels cooler. Okay, so this is the shape of an endothermic graph. Endothermic graphs go up. Now, it's wonderful if you understand why. If you just if you're on a quiz or a test and you're having a brain fart, right? If your brain's just like, ah! If you're, say, going to, City Hall or a library or whatever, just like the stereotypical, big building, would you generally go up to enter or down to enter? Generally, you would go up, right? They've got stairs, there's the stairs to the, downtown Vancouver, they got stairs to the, I don't know, the art gallery and things like that. You go up the stairs, right? Okay, so you go upstairs to enter, usually. Or if you arrive at someone's house, very rarely do you kind of go down, you mostly go up, okay? It's not an awesome analogy. I mean, my parents' house, you have to go down a stair to get to their front door, but, whatever. Okay, endothermic, temperature decreases, it feels cooler. All right, second example, let's say you have some reactants in a chemical reaction and they have 9 kilojoules of potential energy. So now we have these reactants with 9 kilojoules of potential energy. And our products have 1 kilojoule of potential energy. That means, what happened to that extra 8 kilojoules? Where did it go? Eight kilojoules of potential energy, what happened to it? Yeah? Pardon me? Yeah, it turned into heat. It turned into kinetic energy, okay? And so now, are the particles moving faster or slower? They're moving faster, and so the temperature goes up. And if we were to write just a generic exothermic reaction, the energy term exits the reaction arrow. Okay, so we would have A goes to B plus energy. Is good? Which way is the potential energy graph going to go? Is it going to go up or down? Potential energy graph is going to go down. Okay, so here we have, and notice the total energy before is staying the same as the total energy afterward. We have our potential energy here, direction of reaction there. Sometimes it's also called progressive reaction. Doesn't really matter. The reactants are higher potential energy. The products are low potential energy, and kinetic energy is released. Okay, I think that's it for this. Bloody, bloody, blah. Blah, 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 blah. And we have no more time, so I think. So you're going to do 6.4a. I would also like you to do page 110. No, never mind. Just do 6.4a. Yeah, that'll be good.